Okay, we're picking up where we left off in the previous video, going through this sixth section of chapter 1 in the algebra textbook. In the previous video, we learned about polynomial equations, absolute value equations, and how to solve them. Now here, we're going to look at radical equations. And also, it says equations with rational exponents. What that's about is we're going to be looking at an equation and seeing if we can make a certain substitution for a variable expression, then we could turn that equation into a form that we're familiar with. Like we could turn it into a quadratic equation or a linear equation, etc. So that'll be really interesting as well. So now we want to talk about radical equations, how to solve radical equations. Well, first of all, what is a radical equation? Well, it's an equation where at least one expression or term in the entire equation is a radical expression. But assuming you don't have any terms that are exponentials or logarithms. So you can have rational terms, polynomial terms, but if just one of the terms is a radical term, then you call that a radical expression or a radical equation. And so what is a radical term? Well, that's going to be either a term that obviously there's a radical, but at the same time that's something like a rational exponent as well. Okay, and obviously this can be in any number of variables. It's just if there's one radical anywhere in there, then you have an equation in these different variables, a radical equation in variables x, y, and z, let's say. If there's just one radical somewhere. But again, there's no exponentials and there's no logarithms. Otherwise, the exponential would take precedence in naming the equation, and then the logarithm would take precedence after that. Okay. So it says an equation with one or more radicals containing a variable. So no, just because you have no, this is not a radical equation. It needs to have a variable inside of the radical. Okay. So it says, if an equation with one or more radicals containing a variable is called a radical equation, we can eliminate the radical by raising both sides of the equation to a power equal to the index of the radical. Okay, so that's the idea. Like if you had x, the fourth root of x cubed is equal to 2, right? Well, if we raise this to the power 4 on both sides, what happens? Well, you get rid of the radical. Right? It's like this is x to the 3/4. If we raise that to the power 4, well, 3/4 times 4 is just 3. So if the general idea is we're going to raise both sides of a radical equation to the index of a certain radical to eliminate the radical. And then we're left with just a regular equation in whether it be polynomial, linear, whatever, and we go ahead and solve. Okay. However, as it says here, by raising each side of a radical equation to a power equal to the index, a new equation is produced, yes. Okay, but however, some or all of the solutions to the new equation may not be solutions to the original equation. These are called extraneous solutions. Okay, and so this term extraneous solution, what exactly are they talking about here? Well, this is really going to be, you can look at the term extraneous solution is any of the scenarios that we've worked with so far where you get a solution and you plug it back in and it doesn't check out. Even in the case where, like with a rational equation where it doesn't check out because you're dividing by 0, right? It doesn't have to be the case where we're going to see with absolute value equations, with radical equations, we're going to sometimes put a potential solution back in, and there's no dividing by 0 issue. There's no problem. You simplify and you get 2 numbers. It just doesn't check out, right? Or there's going to be scenarios where you plug a potential solution back in, and you're dividing by 0, or you have a negative under an even root radical, so it doesn't check out that way. Either case, you call that an extraneous solution. It's just any time where after algebraic manipulation, you get some values that appear to be solutions. You didn't make any math errors, but still that solution doesn't check out. That's what an extraneous solution means. Okay, so now where does this come from in terms of a radical equation? Well, it's just from the process of squaring both sides. It's like if we had the principal square root of x is equal to -5. Okay, well, we square both sides. You get x is equal to 25. Is that a solution? Well, no. Plug in 25. That's not a solution, right? It just comes from the ambiguity that when it comes to squaring or taking an even power of something, it's like it's an irreversible process is what they call it. There's some if you ever do something to both sides of an equation that's an irreversible process, then that's when these kind of issues can come up. Okay, but it's not a big deal. It just means you have to, in those situations, you're going to have to check your solutions or be aware that there might be solutions that you lost. You know, like when you divide both sides by x, something x. Well, if x could be 0, then maybe you need to remember, okay, well, what if x could have been 0 originally? Okay, so yeah, for this reason, it's just necessary to check all potential solutions in the original equation. And they give an example like I just gave you, that the principal square root of x is equal to -10. You square both sides, you think you have an answer, but you really don't. Okay, so to solve a radical equation, what do? You isolate the radical. If an equation has more than one radical, choose one of the radicals to isolate, just one. Then raise each side of the equation to a power equal to the index of the radical. Solve the resulting equation. If the equation still has a radical, repeat steps 1 and 2. Check the potential solutions in the original equation and write the solution set. That's the idea. Okay. Now they note that this potential of extraneous solutions only comes into play if you're raising to an even power to eliminate an even index in a radical. If it's odd indexes, it won't matter, but it's still good practice to check your solutions. But technically, if you're only eliminating odd radicals, raising both sides to odd powers, if you don't make any math errors, there won't be extraneous solutions. But notice it says that if there's more than one radical, then you start by isolating one radical on one side, raising both sides to the power of the index, simplifying, solving, and then if you have more radicals, do that same process again until you could just break down the equation. Okay, so let's look at an example here. So, okay, we want to isolate the radical. All right, now raise both sides to the power 2 to eliminate the radical on the left. And then here we're going to get x squared plus 8x plus 16. Now we're left with this quadratic equation here. So subtracting x from both sides and subtracting 10 from both sides, we get this. Now we can do, so let's see, x, 3, 2, or no, 6 and 1. 6, 1. Okay, so x is equal to -6. X is equal to -1. Well, we need to check these. So -6 plus 10 is 4. Principal square root of 4 is 2. So 2 minus 4 is equal to -6. That's -2 that's not equal to -6. So this is not a solution. What about -1? -1 plus 10 is 9. Principal square root of 9 is 3. 3 minus 4 is equal to -1. -1 is equal to -1. So there's the solution, the only solution. Okay, now let's see. Next, let's look at an example like this. So with two radicals is equal to -2. So with two radicals, we just start by isolating one of the radicals. So okay, now we square both sides. And you're going to get, so m minus 1 is equal to, and then so 3m plus 1 minus 2 root 3n plus square root 3n plus 1 minus 2. So you're going to get this, and then plus 4. Okay, so that's m minus 1 is equal to 3m plus 5 minus 4. Okay, now let's add this radical to both sides, this radical term here. Now if you subtract m from both sides, you're going to get 2m. If you add 1 to both sides, you're going to get this. Okay, now we can divide both sides by 2. So 2. Okay, now let's square both sides again. We've got 4 and then m squared plus 6m plus 9. Okay, so 12m plus 4 is equal to m squared plus 6m plus 9. So m squared, 6m minus 12m, then 9 minus 4. Okay, so let's see. We've got 5, 1 minus 5 minus 1. So m is equal to 5 and m is equal to 1. Okay, so now if we plug those back into the original equation, you're going to see that actually both check out. So we're good. And again, the reasons why they might not check out, maybe you simplify and you get two numbers, but they're not the same, or maybe there's a domain issue. Like maybe you get a negative under the even radical. Okay, now, but the next thing we want to think about is solving equations with rational exponents. Okay, these are technically radical equations, right? It's just but we're looking at it from a different perspective. Okay, so here we divide both sides by 2. We're left with x plus 1 to the 2/3 is equal to 4. Okay, but now we have a cube, an nth root or a third root radical. So we want to raise both sides to the power 3 here. And we're left with x plus 1 squared is equal to 4 cubed is 64. Okay, now we can apply the square root property and get x plus 1 is equal to, and then plus or minus 8. So x is equal to minus 1 plus or minus 8. So minus 1 plus 8 is 7. Minus 1 minus 8 is minus 9. Plug those back in. You'll see they both check out. So those are your two solutions. Now, one thing I will tell you that, and you can use this idea for solving radical equations at this point in algebra, is that so if you do ever come across a scenario where you've got like x to the 4th is equal to 16, and you need to solve this, okay? This isn't an actual property, and that an official property they state in algebra, and for a good reason. There's a good reason why they don't do this. But if you're only considering real solutions, okay, if you have x to some even power, the idea of like a number, you're trying to figure out what number to an even power equals a positive number, some even power other than 2. If the power is equal to 2, well, then you just apply the square root property, and even this could be negative if this power is equal to 2. But if it's an even power not equal to 2, and you're trying to think about what number, when I take it, number or numbers, when I take it to this power, do I get this positive number, this even power, this positive number? If you're only considering real numbers, if you're only considering numbers on the real number line, okay, then you can go ahead and do this. You can say, okay, in that case, take the principal 4th root of both sides and put it plus or minus. That's going to work. So here, 2 to the 4th is 16, but also minus 2 to the fourth is 16, and that's the only real numbers that when you take them to the fourth power, you're going to get 16. Okay, but the reason why they don't state this as a property is because, number one, you can't state it in general because for, like, okay, if you put a negative 16, you know, if we were just considering square roots, then you could state it in general because you could put a negative 16 under here and it would still work. But when you, like, okay, this square root property works. Putting the plus or minus on both sides with the square root, like, okay, yeah, this square root property here, if you've got x squared is equal to any number on the right, positive or negative, any number. The idea of putting a principal square root on both sides and putting plus or minus, we're going to see that works across the board for if you had, no matter what you have underneath the square root, complex number, whatever. This works in all scenarios. So it's an official property. Okay. However, when it comes to even roots, there's more for us to break down. So they don't, regarding the different numbers when you take them to the fourth power, you get certain numbers. There's a lot more to study. So they don't state this as a property. However, if you come across a situation where you're only considering real numbers as solutions, and you've got a positive number as what number when you take it to an even power do you get a positive number, then you can do this. There's going to be just two numbers. Like you can put the principal nth root and put the plus or minus out front. That's going to work. Okay, now this last section, it says solve equations in quadratic form. And this is really interesting because this is really a general kind of technique that applies. It's not just about any equation in quadratic form. You want to be looking for any problem you're solving in math. You want to be on the lookout for similar patterns, similar forms. Okay, and specifically the idea that, okay, if I made a substitution here, if I said that like this new variable was equal to some expression, could I put what I'm looking at into a form that I'm familiar with? So what I mean is this. So if we look at the example that they give here, okay, 2 plus 3 over x squared minus 2 plus 3 over x minus 12 is equal to 0. Okay, so you could look at this at first glance and think, okay, this is a rational equation. Let me expand everything out, combine like terms and put it into that rational equation form, and then solve it like a rational equation. And that's fine. You could do that. But if you want to be on the lookout in all scenarios for similar patterns, similar forms, similar features that you're familiar with. So if you look closely here, you might look at this and say, well, if I said that some value u, like a new variable u, was equal to 2 plus 3 over x. Okay, now let me make that substitution. What happens? Okay, well, I'm going to get u squared minus u minus 12 is equal to 0. Well, that's pretty interesting. This is now I have a quadratic equation that I know how to solve, right? And this seems pretty simple. I can solve this and then just back substitute, and you can absolutely do that. And so that's the idea. You want to be on the lookout for, if I make a substitution for some variable expression, could I put what I'm looking at into a form that I'm familiar with? And it doesn't have to be a quadratic equation. It could be anything. So if we look at this example here, you have 2x squared minus 3 squared plus 36 times 2x squared minus 3 plus 35 is equal to 0. Okay? Well, we can see that if we said that u was equal to 2x squared minus 3, then what do we get? We get u squared plus 36u plus 35 is equal to 0. Okay, so we can factor this. We can have u 35 1 is equal to 0. So u is equal to minus 35, and u is equal to minus 1. Okay, but u is equal to 2x squared minus 3. Okay, so if we add 3 to both sides, we get, okay, divide both sides by 2. You get x squared is equal to minus 16. So x is going to be plus or minus 4i. Okay, now here 2x squared minus 3 is equal to minus 1. So 2x squared is equal to 2. X squared is equal to 1. So x is going to be equal to plus or minus 1. Okay, and so it doesn't look like we're going to need to do any to check the solutions if we didn't make any mistakes. There's no, this was all kind of just quadratic equations here, but you could still go check the solutions and see that these are going to be the 4 separate solutions here. Yeah, there you go. Okay, let's look at another example. 2w to the 2/3 is equal to 3w to the 1/3 plus 20. Okay, here we can see a pattern in that if we said that u was equal to w to the 1/3, then u squared is going to be equal to w to the 2/3. So we have as 2u squared is equal to 3u plus 20. So 2u squared minus 3u minus 20 is equal to 0, and you can go ahead and solve that, and you get 2 values of u, which then you can plug w to the 1/3 back in, solve for w, and you get these 2 values of w. Okay, and now, but you didn't have to raise both sides to any even powers in the process, so those solutions are going to check out no matter what if you didn't make any math errors. And so, yeah, that's the general idea of looking for similar forms or patterns that you can make a substitution and convert something to something you're familiar with.